You look just like they said. My boys will be immensely pleased by that introduction. Thanks. Am I on the screen? So in one of the many pearls of wisdom in Gerald Weinberg's great book, Secrets of Consulting, is one that he calls Rhonda's First Revelation. And Rhonda's First Revelation says, it may look like a crisis, but it's only the ending of an illusion. The field of software engineering originated in the middle of what was called the software crisis. In the 60s, as software projects got bigger and more complicated and more ambitious, by the standards of the time, they also got more difficult to control and manage and predict, and they would fail in various ways, and that became more common. And so NATO, of all things, called people from industry and academia, practitioners and theorists, a whole big group of people to Germany for the first software engineering conference in 1968. And it actually got off to kind of a promising start, but then for various reasons that I won't go into in detail, kind of went wrong. And the result was that we labored under 30 years of this. That's a little unfair because the software engineering folks did realize some of the limitations of waterfall and they tried other things. But to my mind, all of the traditional software engineering processes sort of suffer from the same fundamental limitations that waterfall did. And so things were pretty unpleasant in the software industry or in large parts of the software industry for about 30 years until the late 90s when the Agile movement came along and related that, practitioners and programmers began kind of taking ownership of the processes and methods they used and how we deliver software. And things got a lot better. But the sort of failure of the traditional software engineering ideas have given rise to another crisis. A couple of years ago, Tom DeMarco, who in some ways was one of the fathers of software engineering, published this article where he suggested that the idea of programming as an engineering discipline was a failed idea that just needed to be abandoned. Closer to home, my colleague Bruce Williams back there early last year tweeted this: "I am not an engineer and neither are you." I doubt you're an architect either. Both of these crises, the original software crisis that led to the software engineering field and then the sort of crisis now of, oh, we're not engineers and maybe what we do is incompatible with engineering and we should give up on that idea, are really driven by the same illusion. A thorough misunderstanding of engineering and what it is. And this was my response to Bruce. It's a little more curt. Oh, I love you too, Bruce. It's a little more curt than maybe he deserved, but I was busy. So let's talk about engineering for a little bit and what it is. When you talk about engineering to people who don't have an engineering training and background, they tend to think of this list of things, kind of. Engineers do a lot of modeling and mathematical modeling and formal analysis of those models, and they write a lot of documents, designs and plans, and they specify everything to the nth degree. And the goal of all of this is that the product of engineering is safe and reliable, and that the engineering project is predictable, budget and time and quality and all those things. Also, if you mention engineering to people who don't have an engineering background, they tend to think of civil engineering, or more particularly large-scale structural engineering, bridges and highways and things like that. And that's kind of a natural thing. Those things are obvious. They're kind of easy to understand how you'd go about, you might not know how circuits or chemical processes work, but you can conceive of how you'd go about building a bridge. And we trust our lives to those things every day. So that's what people tend to think about. And if we take that list of things people think about when they think about engineering and apply it to civil engineering as a kind of checklist, how does it work? Well, do they do a lot of modeling? Yes, they do. Do they do mathematical modeling and analysis and formal analysis and specification and verification of those models? Yes, they definitely do. And they definitely write a lot of documents and designs and plans and all those things. Are they safe? I don't want to at all suggest that bridges and civil engineering projects aren't safe, because by and large, and to an extreme degree, they really are. However, with some regularity, every few years, there are failures of civil engineering projects. So while these projects are largely safe, it's not a guarantee. Sometimes they fail to be safe. As for predictability, if you're involved in local or state government at all, or pay attention to those things and look at the procurement processes, you know that the idea that civil engineering processes are predictable is kind of an illusion. Often there are big cost and time overruns. To the extent that they are predictable, it's the construction process itself and not the engineering process that's often the predictable part. And also, to the extent they're predictable, the credit for that goes to good old-fashioned project managers, not the engineers. So that's kind of an illusion. So, you know, 3.5 out of 5 or 3.9 out of 5 I'll give them for civil engineering. But there are a lot of other kinds of engineering. Civil and structural engineering, aerospace, mechanical. These are just a few of the kinds of engineering that are out there. And I've kind of ordered this list from sort of big-scale things and big-scale concrete things, not necessarily cement-style concrete, but physical, tangible structures, down to more small-scale, sometimes abstract things. And as you go down this list from the large-scale concrete things to the smaller-scale abstract things, the rules change a lot. And as you get down into chemical and industrial and electrical engineering, the costs are much less dominated by materials and labor, and they're more dominated by the cost of the design process and figuring out what you want to do and exploring alternatives and things like that. So, for example, if we apply that same checklist to industrial engineering, it looks pretty much the same, but there's a big piece missing. How many of you know, people in the front, and people in the back, don't bother raising your hands so I can't see you at all. People in the front, how many of you know what industrial engineering is or have a good idea of what that is? Anybody? Just a few, it looks like. So industrial engineers design and optimize processes. And often that's factory processes. Industrial engineers design assembly lines. Often they design in collaboration with mechanical engineers factory machinery. So just to give you an example, if any of you have ever been into a Krispy Kreme donut shop and seen the mesmerizing automatic donut machine, that is really the product of industrial engineering collaborating with mechanical engineers. How much mathematical verification and modeling and analysis do you think went into the design of the Krispy Kreme donut machine? Not much at all. It was almost certainly an iterative sort of tinkering project in the workshop, putting stuff together and trying it to see if it works, and wow, the dough really sticks to these little bars here. We got to figure out a way around that. So it doesn't fit that sort of definition of engineering that that most people tend to think about. And that's really nice. My confidence timer box is upside down. It's going to be hard to read. So if I go over by like an hour, that's why. So there's something missing from this, which is that they do prototyping. As you work down that scale and towards the more abstract kinds of engineering, they tend to be more test-driven, if you want to use those terms. We have an idealized view of engineering, and we tend to think of it as sort of very sophisticated and planned and predictable and well thought out. And we tend to, if we see something that's rough-hewn and sort of something you could build in your garage or something, an idea your kid would come up with, we don't tend to think of that as engineering and sneer at that kind of thing if it doesn't solve the problem completely in a very technical way. Sometimes, though, engineering is just kind of workshop stuff and common sense, and it doesn't solve the problem completely in a complicated way. It solves it mostly in a simple way. A good example of that, the aerospace engineer Eugene Ferguson tells the story of his first engineering invention when, as a boy, he took a trip to the airport and saw in 1937 a Douglas DC-3 land for the first time. And he observed what all of us have seen either in person or in movies, the Plane comes in, as it touches the runway, the tires, which are not rotating yet, hit the runway, which relative to the plane is moving fast, and they screech and there's smoke and the plane bucks as it spins the wheels up and everything else. And he thought, well, that's kind of kludgy and crappy, and it's potentially dangerous because the wheels could blow out, and that's a particularly fragile time for the airplane as it's first hitting the ground. So he went home and sketched out a design for a mechanical device to spin the wheels up to approximately the airplane's ground speed just before touchdown, and he sent this proposal off to the Douglas Aircraft Corporation. And he relates the story of getting a note from, presumably the vice president in charge of crank proposals from school children. And he explained that this was actually a well-understood problem, and it had a name called pre-rotation. And there were numerous proposals that had been floated for how to pre-rotate tires. And all of them involved adding weight to the airplane and to the landing gear, and that weight would be better used increasing the tread thickness of the tires. And Ferguson goes on to say that that experience taught him that every technical problem has alternative solutions, often several. One that was not obvious to me was the Douglas solution, to reject solutions that required more machinery and to use the weight saved to make a simpler system more robust. As an aside, I think any of us in this room who, before coming to Rails, worked with web development in Java frameworks will have no problem seeing Rails as something of a Douglas solution to the problem of web development. So anyway, to engage in a bit of public gloating, eventually Bruce responded with this, by the way, Glenn, you changed my mind about software engineering. What's next, architecture? And my response at the time was, no, I'm not going to touch software architecture with a 10-foot pole, but about 3 months ago, somebody gave me this business card. So I guess I kind of have to think about software architecture now. But in any case, we all, most of us anyway, misunderstand engineering. And to some degree, even engineers have an idealized view of what engineers do. We understand concrete things better than abstract things. And so we look at the obvious, tangible things that engineers do, and we think those are the fundamental things. But really, the documentation and the math and the modeling and stuff aren't the fundamental parts of engineering. And there are very few engineering books that talk about this, but if you're interested, just a quick recommendation, 2 books, What Engineers Know and How They Know It by Walter Vincenti, and Engineering in the Mind's Eye by Eugene Ferguson, the guy who told the DC-3 story, are well worth reading. So, I hope I've made a little bit of a case that really programming kind of fits into engineering, somewhere along that continuum down near the abstract side of things. But let's talk about programming a little bit. Programming does differ from the other engineering disciplines in 2 really important ways. And one of those is that, I'll talk about one first. The software engineering field, the way it was originally conceived, was designed by an analogy with more traditional engineering disciplines. And the analogy goes something like this. In traditional engineering disciplines, you have engineers. And those engineers are tasked with producing designs which they draw or write down on paper. And those designs are handed to laborers or construction workers who build the finished artifact. And if that's what the process of engineering looks like, then what would the process of software engineering look like? It seems pretty simple and obvious, right? You have engineers, maybe even the same guys, just retrained, and they produce a design and write it down on paper, and they hand it to laborers who toil in their cubicles and produce the finished artifact. And people kind of went with this analogy for a long time, even though it didn't really work very well, until about 1992. Some people had realized this before, but a guy named Jack Reeves in 1992 published an article that said, we got this all wrong. And the key to the problem, to realizing there's a problem, is that second slot there, second part of the process. We have never figured out a way in software to specify a design in a way that's clear enough and thorough enough and, we can reason about enough to know that it's correct, and then hand to programmers, and they can produce the working system with any kind of fidelity to the original design without redesigning and adding that to that design and all those things. So he said, work with me on this and try a thought experiment. Let's get rid of that design document and teach the programmers to think of themselves as engineers and do things that way. And you know, that source code, that's not really the finished artifact. That's not what customers are paying for. They're paying for deployed systems running on real machines and solving their problems. That source code is actually the design of the software system. Maybe not the whole design. It's still sometimes useful to have diagrams and high-level overviews and introductions to part of the system that can be read without looking at source code. But when it comes to the detailed design of your system, the source code is it. So then what do we fill the third slot with? Anyone? Close? Well, that's the fourth thing. That's the artifact they're paying for. What's the third slot? Compilers, programming language implementations go there. And then you end up with running software, which is what customers actually want. Reeves pointed out that there is a really big difference between these two things. The analogy still works, right? But all of a sudden the costs are upside down. The third step in the top row is by far the most expensive. It dominates everything in structural engineering, the cost of material and labor. And as a result, they have all kinds of tricks to avoid spending money on building prototypes and testing them. And in fact, we tend to think of mathematics and formal analysis as a tool that the engineering disciplines use for achieving robustness and safety. But if you look at the history of the fields, mathematics and formal analysis were introduced as a cost-saving measure, because if you can build a model that approximates reality and do some analysis on it, you can reduce the amount by which you over-engineer and reduce the cost of materials. So the third step on the top row is by far the costliest and the most time-consuming. And the third step in our field is by far the cheapest and fastest. And that changes everything we do. And that's why the proper engineering approach to software is not to load the front of the process with a bunch of analysis and inspection and verification, but rather to be iterative and build many prototypes of our design and test them. Okay? Let's focus in on this a little bit more. Is there a model here? I'm not going to be able to hear you unless you yell. Is there a model here? Maybe. That's actually a pretty good answer. In the best case, yes, there's a model visible in the source code. Is there a document here? The source code. Is there math here? Yeah, it's the source code. Computer programming languages are formal languages, and some of them even have mathematical specifications. We're at a Ruby conference, so we don't have that. But still, Ruby is executable math. All those things are there. It just doesn't look quite like it looks in classical engineering. And let's focus on the document issue in particular. There have been all kinds of proposals for how to document the requirements and specifications of software systems. I want to show you 4 documents. They document a very simple process because it had to fit on a slide. But here are 4 documents. A JUnit test, an RSpec example, a cucumber scenario, and a fitness test table. Those are all documents, and they're all specifications, but they're not merely documents. In the classical engineering disciplines, where they have to work with physical materials, they're not working with pure abstraction and pure information, they have to work with mere documents. We get to work with documents that are more than just documents, but they execute and verify themselves and verify an implementation against those specifications. We get a huge benefit from that. And any process that purports to be a software engineering process and doesn't acknowledge the upside-down economics where what's expensive in traditional engineering disciplines is the cheapest part of our work, and that doesn't deal with the fact that our documents and our math can execute and do real work for us, is not acknowledging the realities of our field. So I mentioned that engineering is different from, that software is different from other engineering disciplines in two important ways, and one of them is this upside-down cost model and the nature of what we do. The second one was pointed out to me by a guy who wrote to me named Zane Bitter. One thing electrical engineers do not do is to sit around pontificating about whether electrical engineering counts as real engineering. I suggest that we should choose to be just like the traditional engineering disciplines in this respect, at least. Now there's a third crisis. Would we prefer to be engineers, or would we prefer to think of ourselves as craftsmen? And if we consider ourselves engineers, what is the role of craft in what we do? And if we love being craftsmen, can we still think of what we do as an engineering process and be that disciplined about it? Not that craftsmanship isn't disciplined. Let's think about the difference, to the extent there is one, between craftsmen and artisans and engineers. And since we've been talking about documents, let's focus our discussion on documents for a minute. An artisan or craftsman may, doesn't have to, but may produce documents to help themselves think. But then they build what's in their heads. That sounds an awful lot like what we do, except then when we build what's in our heads, it turns out to be a document too. Engineers, on the other hand, must produce documents. Well, they produce documents to help themselves think, but they don't have a choice in the matter. They must produce documents to convey the design to builders, and that's the primary purpose of those documents. And that's because the engineers are not the builders of the things they design. They're divorced from that. And a lot of that divorce comes from, again, the need to deal with physical materials, sometimes at large scale. It might be more than one person to do. The skill set for designing the thing and actually building it might be different. So they have to convey that design to the builders. But for a minute, let's look at some models and documents that engineers produce. And we're going to start at the top of that list I showed earlier, civil and structural engineering, and work our way down to the more small-scale abstract kinds of engineering. Bending moment equations and models for bridges, handwritten sometimes, more formal sometimes, a bending moment diagram. Notice that these models bear very little resemblance, except in a very abstract way, to the artifact that's being built. But then you get to aerospace engineering, and there's a lot of that same kind of thing, but there's also models that at least are physically accurate for the envelope of the structure, so you can test it in wind tunnels, and aerospace engineers do a lot of wind tunnel testing with models that look like what's ultimately going to be built. And mechanical engineers. When you get down to electrical engineering, things are more abstract still. And apart from the fact that it's usually three-dimensional structures or 2.5-dimensional structures compressed onto a two-dimensional sheet of paper, this is starting to look very much like the artifact they're actually building. As the engineering discipline becomes more abstract, the models can become more concrete. And then there's software. How much of a resemblance does this bear to the thing that's actually built? Well, if you want to think of it in terms of bytes and registers running through the CPU and the instruction pipeline and all that stuff, given that this is in an object-oriented language and CPUs aren't object-oriented at all, this doesn't seem to be much of a correspondence. But the designers of programming languages, with the possible exception of some of the languages we saw last night, make sure that there's a perfect isomorphism between the constructs in the language and the constructs that get run on the computer. So in some sense, this is exactly the artifact that gets built. And it feels like that to us when we're writing this code, doesn't it? We don't think about that transformation to sets of instructions and data stored in memory locations and loading things into registers. We think about classes and methods and variables and the constructs we work with in code, and we know that the compiler or the interpreter will take care of maintaining that isomorphism so that what we write gets executed just like that on the CPU. Software engineering is the most abstract of engineering disciplines, and our models are the most concrete for what we do. Another interesting thing about engineering modeling is that as computers and software have become more powerful, even in the traditional engineering disciplines, their models have started looking less mathematical and more like simulations. And so it turns out to be cheaper and more effective, in many cases, to build a simulation-style model, a prototype in software, if you will, than to formally model things as systems of equations. And so in electrical engineering, you have circuit simulators that help with the circuit design process. And CAD/CAM systems that can do more than help you draw things, but automatically take parts through all their degrees of freedom and check for collisions and possible abrasion between parts that would interfere with the working of the machine. And fluid dynamics modeling of how landing gear affect the airflow around an airplane as it gets close to landing. Propeller dynamics, statics modeling of bridges, and also, for purposes of traffic engineering, which is another engineering discipline, modeling of airflow around structures to see how that will affect cars on roadways and pedestrians and things like that. So software is changing the way traditional engineering disciplines are working and allowing their models to be less abstract and more concrete in similar ways to those that ours are. So, about to conclude. Software models. Because our artifact is abstract, our models can be concrete in the sense of feeling like we're working with the real thing. The model is isomorphic to the built artifact. There's a direct correspondence between what we write and what gets executed. And I can prove that because, as Dave Thomas and Andy Hunt pointed out in The Pragmatic Programmer, it's never really a compiler bug, right? The result of these things is that modeling feels to us like working directly with the runtime constructs. And we feel those things as we work with them. Corey, are you still here? No, he had to go. So Corey has been tweeting recently about the software he's currently building pushing back on him and telling him that it needs to be designed in a different way. And sure enough, he tried that and it was way better. How many of you have a physical sense of the objects and values and things that run through the software you're building as you're building it? Anyone? A lot of us. We have a spatial model and it feels like we have our fingers in that thing. It's totally a construct of our brains, but that's the way it feels to us. And because of the nature of software, we're not isolated from the building process of our things. We're the designers and the builders. The compilers just do the grunt work. To us, it feels like we're building the end product. And furthermore, we are also writers. Our code must serve two purposes. It has to be the solution, and it has to describe the solution. It can do both of those things in one document. So, brief digression here. The cinematography technique you're about to see is called racking focus. And in this technique, the director and the photographers arrange for something important to be in the scene from the beginning, but out of focus, So our attention is not drawn to it, and most viewers won't see it at all until the focus changes and brings what was previously invisible to our attention. Now in this scene from the Spider-Man is such an extreme case that it's really just an optical trick. Unless you knew that spider web was there and knew to look for it, you couldn't possibly see any part of it. Usually the technique is more restrained. Here's a scene, and it's going to be a little bit dark on these screens. I apologize. This is a scene from the old 1980 movie, The Stuntman. And Peter O'Toole is visible from the very beginning of this scene in the background, and he's even recognizable because he's such a distinctive-looking man. But most viewers of this scene wouldn't notice him until he's brought into focus and your attention is drawn to him. What we focus on matters. And the things we don't focus on can completely escape our attention. And the fact of the matter is, in software, some things are easier to focus on than others. One of my favorite quotes about software is this one from Abelson and Sussman: "Programs must be written for people to read and only incidentally for machines to execute." I love that. I use it all the time. I think about it all the time. If you take it at face value, it's utter crap. We don't get paid for programs that people read. We get paid for programs that execute on machines and work and do useful stuff. And, sometimes people kind of miss the point with this, and they do take it literally. And one of those is a dear friend of mine, Dan North, who recently wrote, software practitioners often fall in love with the software itself and start thinking of themselves as craftsmen of software. And he went on to describe how this is a bad thing because, of course, nobody pays us for those internal things. Nobody pays us for source code that's fun to read. They pay us for code that works. But, I love you, Dan, but Abelson and Sussman are engaging in a technique you may have heard of called hyperbole. And they're exaggerating a little bit to make a point. Somebody who makes the same point in a more straightforward way is Donald Knuth. Let us change our traditional attitude to the construction of programs. Instead of imagining that our main task is to instruct a computer what to do, let us concentrate rather on explaining to human beings what we want a computer to do. See, the difference is not, whereas Abelson and Sussman talked about we shouldn't do this, we should do that, Knuth is talking about where our focus is. And it's really important that our focus be there because our systems have this internal and external dichotomy. The internal things, the internal quality of our systems, its internal structure is abstract. And the external behavior is concrete, and our customers notice it and draw our attention to it. The internal things are hidden. And in fact, only we can perceive them because you have to understand software and be experienced with it in order to look at those things and see whether it's good or bad in many cases. But the external qualities are public and visible. And finally, the internal qualities have potential effects that may or may not come to pass, and your expertise can help you judge the likelihood of that, but the external qualities have immediate effects that your attention is drawn to now. But that doesn't mean those internal qualities are not important. And they're important because they do have those potential effects that can bite us or reward us later. But in order to do a good job with those things, we have to focus on them. Because we're working with pure information, pure abstraction, because we are writers, because we are creators and designers, we have the luxury of being both engineers and craftsmen. We're both designers and makers. We are not insulated from the artifacts we're designing. And like craftsmen, we can feel the things we build, and its quality affects us emotionally. We have this luxury. And we also have a responsibility to be not just craftsmen, but also engineers, because otherwise, or to be craftsmen and not just engineers. It's a luxury and a responsibility, because otherwise we would inevitably lose sight of the less tangible but no less important aspects of our creations. Thanks very much.